Welcome back to this lecture on proof by cases. In this fourth and last segment, we're going to consider a special case of proof by cases called an exhaustive proof. And here is the definition. An exhaustive proof is a special case of a proof by cases in which each case only involves checking a property for a single element of the domain. Now remember, in the previous proofs by cases, a case was, for example, such number is even. Well, that covers an infinite number of elements in the domain. In fact, it covers half of the integers. That was not a proof or an exhaustive proof by definition. But in some cases, it's possible to limit each case to a single element of the domain, and that's what we're going to show here on this example. So theorem number 3 for this lecture states that the equation 2 times m squared plus 3 times n squared is equal to 22 has no solution in positive integers. So let's make sure we understand what the statement of the theorem means. It says, you can't find any pair of positive integers for m and n such that when you square m and multiply by 2, and then you square n and multiply by 3, and you add these two results, you get a total of 22. The theorem says there is no way you can find any pair of integers, m and n, positive integers, that satisfy this equation. So the first thing to realize is the domain for m and n is actually the set of all integers, as in most cases so far. So it's an infinite domain. So how could we ever write a proof by cases where each case only involves a single element of the domain? It looks like we would have to do or complete an infinite number of cases. Well, that's true on the surface, but I'm going to show you on this slide how by a little bit of thought and reflection and analysis of the problem, you can process or you can reduce this problem to a situation where you can actually perform an exhaustive proof on it. So let's write an exhaustive proof for this theorem. Let's focus first on the domain or universe for the variables m and n. From the statement of the theorem, we can already reduce the domain to the set of positive integers, namely the integers starting from 1 and going up. We don't need to consider the other half of the integers, the negative integers, or 0. The problem is this domain is still infinite. Now remember, to apply an exhaustive proof, each case must involve only one element in the universe. So clearly we can't have an infinite number of cases, so we need to cut down the domain for m and n significantly from what we currently have. And the way to do that is to analyze the theorem and what it means. What it says is that you're adding two numbers, each of which must be positive, because you're adding a squared number to another squared number. So you're adding two positive numbers and their sum must equal 22. So in particular, what that means is if you have a solution for m and n, if you want to increase the value of m in that solution, you must be decreasing the value of n because the sum at the end must remain equal to 22. So in particular, the larger the value of m, the smaller the value of n if these are solutions to the equation. So we already know the minimum value for both m and n is 1. What we're going to do next is to try and determine the maximum possible value for m and n. And hopefully that value is not too large, so we end up with a small domain. So what is the largest possible value for m if m and n are solutions to this equation? Well, again, the largest value for m will be obtained for the smallest value of n, and the smallest value of n is 1. So let's plug that in here. 3 times 1 squared is 3. If we subtract 3 from 22, we get 19. So what does that tell us? That tells us that whatever 2 times m squared is must be less than or equal to 19. Otherwise, you would go over 22 for the total, and you would never solve the equation. Now, with this inequality, we are able to find out the maximum value for m that satisfies it. Now we know the minimum value for m is 1, so let's start with it. And clearly m equals 1 works because 2 times 1 squared is 2, that's less than 19. Does 2 work? Sure, 2 times 2 squared is 2 times 4 is 8, that's also less than 19. How about m equals 3? 3 squared is 9, 2 times 9 is 18, that's still less than 19. But then you realize that m cannot be equal to 4, because 4 squared is 16, 2 times 16 is 32, that's way over 19. That means for any value of m, 4 and larger, you will never find a value of n for which, when adding those two numbers, you reach the total of 22. So we just cut down the domain for m to actually 3 possible values, 1, 2, and 3. Now let's perform a similar analysis for n. We already know the minimum value for n is 1, but what is the largest possible value for n? Well, this value is reached again for the smallest possible value of m, which is 1. So what happens when we plug in the value 1 for m in the equation of the theorem? We get 2 times 1 squared, which is 2, plus 3 times n squared equals 22. Well, here what we're going to do is we're going to increase the value of n and see what the largest possible value of n is until we reach 22. So we don't want to go over 22, and that's why I write this as an inequality here. Now we can rewrite this inequality by subtracting 2 from both sides to get 3 times n squared is less than 20. And with this inequality, we're able to determine a maximum possible value for n that will potentially satisfy the equation. So of course the smallest value to start with is 1. 3 times 1 squared is less than 20. That's good. 3 times 2 squared is 3 times 4 is 12, which is less than 20. But as soon as we get to n equals 3, notice 3 squared is 9. 3 times 9 is 27, which is more than 20. So that means no value larger than 2 are possible for n if those values were going to be a solution for the theorem here. And again, that's assuming the smallest possible value for m, which is 1. If m happens to be even larger, it's possible that even these values of n are not going to work. But we would just conclude it from this analysis is that there are really only 3 possible values for m and only 2 possible values for n. So when we combine those, we get 6 possibilities, which now allows us to perform an exhaustive proof, which was not possible when the domain was infinite. So to conclude this proof, we just need to go through the 6 possible cases we just identified. So to make sure we are completing a correct exhaustive proof, we're going to consider the cases in order. The smallest possible values for m and n are 1, so we're going to take this as case number 1. We plug these values into the left-hand side of the equality. 2 times m squared plus n squared equals to 5, in this case when m and n are both equal to 1. And of course 5 is different from 22, so we just proved the result for the theorem in one of the possible cases, that there is no solution in this case. Let's move on to case 2, where m is still 1, but n is equal to 2. When we plug these values into the left-hand side of the equation, we get 14, which is again different from 22. So there's no solution in that case either. Case 3, m moves up to 2, n is equal to 1. The left-hand side of the equation is 21. Again, that's different. It's 11, which is different from 22. When m equals 2 and n equals 2, the left-hand side equals 20, still different from 22. So notice we have no solution in the first 4 cases. We got 2 more cases to consider. The next one is for m equals 3 and n equals 1. In this case, the left-hand side equals 21. That is definitely different from 22. So no solution to the original equation in this case. And finally, in the last case, where m equals 3 and n equals 2, the left-hand side of the equation adds up to 30, which is also different from 22. So in conclusion, we inferred that there were only 6 possible cases to satisfy this equation, and we just demonstrated in each one of these cases that there are no solutions in either one of them, and that concludes our theorem. So this was an example of an exhaustive proof. Again, to apply this technique, you must do a proof by cases, but each case must be or must apply to a single element of the universe. In other words, you must reduce your domain to not only a finite universe, but it better be a small universe if you don't have to have too many cases to consider. With this example, we conclude our lecture on proof by cases. Make sure to remember the template for proof by cases and the reasons why it works. Make sure to detect a situation where it's a good idea to apply this technique, and make sure to apply it correctly when you do. And finally, keep in mind that an exhaustive proof is a special case of a proof by cases.